Welcome back to the Deep Dive. Our mission, as always, is taking that really dense source material you send us, the config guides, the deep dive papers, and pulling out the insights you can actually use. So today, we're focusing on two absolute cornerstones of local networking: Rapid Spanning Tree Protocol, RSTP, and Layer 2 Ether channels. The sources you shared, they skip right past the high-level theory, yeah? They go straight into interpreting the command line interface. We're really looking at those configuration kind of quirks and operational details, the things that take you from just understanding a loop-free, high-bandwidth network to actually building one that works reliably.
That's exactly it. We're not here just to, memorize commands. The goal is to really get the why behind it all. Why is the root bridge election done this way with that slightly weird math? And how do we bundle links for more bandwidth without accidentally, creating a huge problem like a loop? It's all about reading the output.
Excellent. So we'll start with a bit of the history, how STP had to evolve, which explains a lot about the protocols we use now. Then we'll get into that strange math behind switch priorities. Then look at the safety features, the guards and filters that keep things stable. And finally, EtherChannel, how it boosts throughput but still plays nice with RSTP. Okay, so the history, it's maybe a bit tangled, but you kind of need it to understand why things are the way they are now. The original standard, IEEE 802.1d STP, back from 1990.
Right. It created just one single spanning tree for the whole physical network, the Common Spanning Tree, or CST, that was purely about preventing loops. Full stop.
But then came VLANs, virtual LANs became huge.
Exactly, and that created a problem. If you only have one tree, you block one redundant path for everything. So you couldn't really load balance effectively. Send VLAN 1 traffic down link A and VLAN 2 down link B. Nope, one link was just blocked.
So Cisco saw this limitation and stepped in. They came up with their own solution.
PBST Plus, per VLAN Spanning Tree Plus. That was the breakthrough. It gave you one spanning tree instance for each VLAN. Suddenly, load balancing across redundant links was possible. Huge deal.
Okay, so that solved the VLAN issue, but then the IE updated the standard itself.
Yeah, with 802.1W, which is RSTP, Rapid Spanning Tree. Much, much faster convergence. But critically, the IE standard was still defined as a single tree protocol.
So Cisco had to merge things again.
Pretty much.
Yeah.
They took the speed of RSTP and combined it with their per VLAN approach. And that gave us Rapid PVST Plus, or RPVST Plus feel. And this is key for anyone managing networks today. Modern Cisco switches, they usually default to RPVST plus Vander. The options you typically get are RPVST plus VEAN, maybe the older PVST plus VAN, or the IE's MSTP, which handles multiple VLANs differently. But the original single tree STP or RSTP, you often just can't configure them anymore.
So RPVST plus is basically the default we live with. It's the practical standard now.
Got it. Okay, let's tackle how switches decide who's boss. The bridge ID, the BAD. Right. It's pretty straightforward at first glance. A 2-byte priority number, plus the switch's 6-byte MEC address. Lowest beat wins the election, becomes the root bridge.
But it's not quite that simple, is it? Especially with PVST+.
No, exactly. That 2-byte priority, originally just a 16-bit number from 0 to 65,535, it got restructured. For PVST Plus and RPVST Plus S, it's split. You have a 4-bit actual priority field and then a 12-bit field called the System ID extension.
And that 12-bit part, that's where the VLAN ID lives.
Precisely. That's the key insight. The VLAN ID gets plugged into those lower 12 bits. So think about it. The switch needs to make sure the priority value you configure doesn't mess with those 12 bits reserved for the VLAN ID.
Okay, wait. So if the VLAN ID uses the last 12 bits, the main priority number has to leave those bits alone. Like, they have to be 0.
Exactly. The iOS needs that separation. The priority you set has to have zeros in those last 12-bit positions before the VLAN ID gets added.
And 2 to the power of 12. That's 4096.
You got it. That's why the configurable priority values must be multiples of 4096. 0, 4096, 8192, 12288, and so on. By forcing these multiples, the switch guarantees those lower 12 bits are 0, ready for the VLAN ID. It's a mathematical constraint baked in to support per VLAN tree.
Okay, that suddenly makes sense of that weird 4096 rule. It's not arbitrary. It's required for per VLAN operation. So we generally want our distribution layer switches to be the root, right? How do we set that up without needing a calculator for the multiples?
Oh, yeah. Thankfully, there are shortcuts. You just use the spanning tree VLANX root primary command. The switch figures out the right number, usually 24576, which is nice and low, and a multiple of 4096. And there's root secondary too, which sets it a bit higher, like 28672. It handles the math for you, guarantees the election.
Simple enough. And let's say you're troubleshooting, you run show spanning tree on a switch that's not the root. What confirms that?
You'll see two main things. First, it'll list the root ID, that's the winner's priority, and MSC. Then, it'll list the local switch's bridge ID. But the real giveaway that you're not the root is seeing the root port listed right there. That port is your single best connection back to the actual root switch.
All right, moving on from electing the boss to how the ports behave. Quick recap. The root port is the best path back to the root bridge, lowest cost. Other active ports become designated ports. And quick operational tip, even with RPDST plus SYN, the Cisco CLI often says BLK for blocking.
Right, when the real RSTP term is discarding.
Yeah.
Yeah, that catches people out sometimes, the difference between the standard and the implementation.
Okay, let's talk safety nets, especially at the edge, connecting to user devices. PortFast and BPDU guard. These two go together, right?
Absolutely essential pair. PortFast is all about speed for end devices like PCs. It makes an access port jump straight to the designated port role in the forwarding state. Skips listening, skips learning, boots up faster.
But faster isn't always safer.
Definitely not here. If you accidentally plug another switch into that PortFast-enabled port, instant loop, because it skipped the checks.
Ouch. Okay, so that's where BPDU guard comes in.
Yes. It's the safety mechanism for PortFast.
Yeah.
Enable both. If that PortFast port ever receives a spanning tree packet, a BPDU, from another switch, bam, BPD guard kicks in, boom, shuts the port down, puts it into the air disabled state instantly.
Disabled. That's serious. The port's basically offline until someone fixes it.
Pretty much. Needs manual intervention or maybe an auto recovery timer if you've configured one,
Yeah.
but it stops the loop cold.
So if you're looking at the output, say show spanning tree, how do you know PortFast is active on an interface? Is there a specific flag?
Yeah, there's a key indicator. In the type column for the interface, you'll see PDP edge. That edge part explicitly means PortFast logic is running on that port. It thinks it's connected to an endpoint, not another switch.
Got it. PDP edge. Okay, now, BPDU filter. This one seems to cause a lot of confusion because it has two modes. There's a conditional one.
Right, the conditional one is usually the safer default. You configure it globally. It only applies to ports that already have PortFast enabled. What it does is it sends a few initial BPDUs, then stops sending them. But crucially, if that port receives a BPDU, the filter logic turns off, PortFast gets disabled, and the port goes back to behaving like a normal STP port. It's like a safety valve.
Okay, conditional sounds. Conditional. What about the absolute filter? You set that per interface.
Yes, and absolute means absolute. It's configured right on the interface, and it just drops everything. It discards all outgoing BPDUs and ignores all incoming BPDUs on that specific port. It basically disables STP entirely on that link.
Whoa, why would you ever do that? That sounds incredibly dangerous.
It is very dangerous if used incorrectly. The use case is rare, maybe connecting distinct STP domains temporarily without them interfering, but the warning has to be really strong. Use absolute BPDU filter on a redundant link, and you've just bypassed all loop prevention. You're asking for trouble, a network meltdown, potentially.
Yeah. Okay, duly noted. Avoid absolute unless you really know why. So BPDU guard protects the edge.
What about protecting the core, the root bridge itself, from rogue switches trying to take over?
That's root guard. You put this on ports where you never expect to see a superior BPDU, like ports facing downstream switches.
Yeah.
If a BPDU comes in that claims to be from a better root bridge, root guard doesn't like that. It puts the port into a broken BRK state. The output describes this as root inconsistent, often shown as root inc.
And it blocks traffic until the bad BPDUs stop.
Exactly. It protects the rightful root. It recovers automatically once the superior BPDUs go away.
Okay, one more guard. Loop guard. What kind of loop does this prevent? Loop guard deals with loops caused by physical link issues, specifically unidirectional failures. Imagine a link where traffic flows fine one way, but BPDUs stop coming back the other way. If a port that should be receiving BPDUs, like a designated or alternate port, suddenly stops hearing them from upstream, it might mistakenly think the path is gone and transition to forwarding, causing a loop. LoopGuard prevents this. If the BPDUs stop arriving unexpectedly, LoopGuard puts the port into that broken BRK state again, but this time the output calls it loop inconsistent. It also recovers automatically once BPDUs start flowing again.
Root inconsistent, loop inconsistent. I know I've seen those. Usually after someone's made a change during maintenance, knowing what they mean is crucial for quick fixes. Those auto recovery features are good, but you need to interpret that show output fast.
Okay, so we've built a nice, safe, loop-free network with RSTP and its guards.
Right, but loop-free often means blocked links, wasted bandwidth, wasted redundancy.
Exactly. So how do we use those links? How do we get that bandwidth back?
That's where EtherChannel comes in, right?
Precisely. EtherChannel lets us cheat. basically. We bundle multiple physical links together. You can have up to 8 active ones usually. And we tell the switch, treat this bundle as one single logical link. It gets called a port channel or maybe channel group. Now, SDP and RSTP, they only see that single logical port channel. They run their loop prevention on that. All the physical links inside the bundle, they can all forward traffic. No more blocked ports within the bundle.
Brilliant. So how do we set it up? I see there's a manual way. Static.
Yeah, the manual or on mode, just channel group number mode, on, super simple. If you check the verification output, you'll see the protocol listed as just a dash. No negotiation happening.
But usually we prefer dynamics, something that checks settings.
Generally, yes. Dynamic is better because the protocols negotiate and ensure both sides agree on the settings. Less chance of misconfiguration. You've got two main options. Cisco's own protocol, PAgP.
That's port aggregation protocol.
Right. It has modes desirable, which actively tries to form a channel, and auto, which waits passively.
Right.
Or you have the IEEE standard LACP link aggregation control protocol, 802.1ax. Its modes are active, which is like desirable, and passive, which is like auto.
And the rule is, for the channel to actually form, you need at least one side actively trying. One side has to be desirable or active.
Correct. You can't have both sides set to passive, auto or passive. Nothing would happen. At least one end needs to initiate.
Okay, now the hard part. The sources really hammer this. Configuration consistency. EtherChannel seems really picky about settings matching across all the physical ports in the bundle.
Oh, it's incredibly picky.
Yeah.
This is where most EtherChannel problems happen. Speed has to match. Duplex has to match. They all need to be access ports, or they all need to be trunk ports. If they're access ports, the access VLAN must match. If they're trunks, the allowed VLAN list must match. And crucially, the native VLAN must match.
What happens if just one setting is off? Like, say, the native VLAN is different on one link out of 4.
The switch is ruthless. That one physical port with the mismatch, it gets yanked out of the bundle immediately. It's put into a down suspended state. You'll see suspended in the output for that specific physical interface. The main port channel interface itself might stay up, but it's running with reduced capacity because that one link is offline.
Okay, so the port channel showing up doesn't mean all links are actually working. That sounds like a silent performance killer. How do you spot that?
Yeah, you can't just look at the port channel status. You need to dig deeper. Use a command like show EtherChannel summary or maybe show interfaces status focusing on the member ports. The output will clearly show you which physical port is suspended, often marked with an S or P flag depending on the command and iOS version, and usually gives a reason code indicating why it was suspended, like a VLAN mismatch or trunking incompatibility. You have to check the physical members.
Good tip. Okay, connecting back to spanning tree. Does bundling links change how attractive that path looks to RSTP? Does it affect the cost?
Absolutely. EtherChannel automatically recalculates the spanning tree cost for the logical port channel interface. It bases the cost on the total bandwidth of the active links. So a single 1 gig link might have a default cost of 4, but bundle 2 1 gig links together, the cost for that port channel drops to 3. Bundle 4 or even 8 still costs 3 for 1 gig links. It makes the bundle path much more attractive. If you bundle, say, 10 gig links, the cost drops even lower, maybe to 2. STP will naturally prefer the higher bandwidth, lower cost path created by the EtherChannel.
Makes sense. Okay, last piece. Load distribution or load balancing. We want to use all the links in the bundle.
Right, but the absolute #1 priority isn't perfect 50-50 or 2525-2525 balancing of bits. The primary goal is to avoid messing up application flows by reordering packets within a single conversation.
Consistency is key.
Exactly. The switch needs to make sure all packets from one specific flow, like a file download or a voice call, always take the same physical path through the bundle. It uses a hashing algorithm to decide which physical link to use for each incoming frame. You configure the method using the port channel load balance method command.
And the methods look at different things in the header.
Yep, common methods look at source MA, destination MA, or both. Or source IP, destination AFP, or both. You can even get more granular and tell it to look at TCP or UDP port numbers, source, destination, or both.
So the idea is pick header fields that are likely to be different for different flows, but consistent within the same flow.
That's the core principle. All frames from your web download will have the same source at destination IP and port numbers. The hash algorithm sees those same values every time and always sends those frames down, say, physical link #2 in the bundle. No reordering. #tag outro.
Wow, okay. That was definitely a deep dive. We went from the history of STP evolving into RPVST plus Sistani, really nailed down that 49.6 multiplier thing in the bridge ID.
which is all about making space for the VLAN ID.
Right, and covered the safety nets like BPDU guard and root guard, and then got into the nitty-gritty of EtherChannel, why consistency is king, and how load distribution works.
And I think the big takeaway, like the sources kept emphasizing, is really learning to read those show commands, understanding why a port is P2P edge, or why it's error disabled, or why it's showing loop inconsistent. That's so much more valuable than just knowing the config commands. The output tells the story of what the network is actually doing.
Absolutely. Okay, so here's a final thought for you, our listeners, to chew on. We talked about EtherChannel load distribution. The goal is using all links, but keeping flows consistent to avoid reordering. The switch doesn't guarantee perfectly equal traffic spread, though. So given all those different load distribution methods based on MA or IP or port numbers, think about your network's traffic. Do you have mostly server-to-server backups? Or tons of different users hitting one web server? How would analyzing those specific patterns help you choose the best load distribution algorithm to really maximize your bandwidth use, knowing that different algorithms spread traffic differently based on what feels to you the most? Yeah, something to consider for optimization.